Welcome to part 2 of Solving Dynamics Problems Pro Tips. We're going to learn about example 5 now, so go ahead and flip to that. If you're dismayed that we didn't finish example 4 or something like that, remember you can always look at the answer key that's posted in the Google Drive. For example 5, which is a picture kind of like this, it says we're not moving a couch or anything, it's just like a 5-kilogram block. If you like, though, you can think about it as really being like the same thing as what we did in example 4, except, perhaps like we'd shift our arms downward and, push at some kind of an angle. All right, if that happens, now the x and y equations get a little bit more complicated. All right, now I'm going to start the problem from scratch, but just bear in mind it's going to really look a lot like this. The main difference, though, is going to be that since you're applying a force at an angle, the applied force is going to end up appearing in both of these equations, both x and y, because it's not all one direction, it's a little bit of both, right? A little bit of x and a little bit of y. All right, so finishing up my force diagram here. Remember, you're always going to have gravity, and as long as the thing is on a surface of any kind, you're going to have a normal force, which is perpendicular to your surface. In part A for this question, it says that there is no, well, I guess A, B, and C, it says that there's no friction. We're going to actually do the same question really in part 6, or sorry, example 6, with friction. So when we get to that, friction will be added in, and it will go to the left since we're attempting to move the block to the right. Okay, now, when we want to write our sum of forces equations, now that we've got our force diagram all ready to go, our sum of forces in the x direction would look like, well, actually just the x component of this applied force right here. That's it. That's the only x force. Okay, so that there would be F cosine theta. Cosine is what it usually is, right? Unless I do something awful like give you the other angle, then it's going to be cosine. This here is given from the horizontal, so therefore F cosine theta is going to give you the x component. All right. And in this question, we're going to have MA, since in the problem it says there's no friction, therefore it must be accelerating. And later on in the problem, they ask us to actually work that out. Okay, the sum of the forces in the y direction will be noticeably different from the couch example. So when we did this thing with the couch, right, we had the normal force, had gravity, they were in opposite directions, and that's it. We just had normal force minus gravity. All right, now, at this point, you might stop and think for a moment why I would have an extra force in the y direction. So pause the video and ponder if you like. Yes, there's another force in the y direction because this force doesn't go just straight sideways like the force did in the couch question up here. In fact, this force is applied at a downwards angle, and so that means that the vertical component, F sine theta, is also going to be in the mix there. All right, now, I didn't put a plus or a minus here because I have to think about which direction it's going. So if we're applying a force in like the same direction as the normal force, then it would have a positive sign with it because it would be going in the same direction, so it would have the same sign, positive, if it were going in the direction of the normal force. If, on the other hand, it's going down like gravity, then we would have a minus sign like we put for gravity here. In this case, the force is applied at a downwards angle, so it's going to be minus. You could imagine the opposite situation, and we will when we do example 6, where it gets pulled upwards, right? Where this sign would be opposite. That would be the only difference, right? If you apply an upwards angle, really it's just going to apply a force at an upwards angle. It's only really going to change the sign of that particular component. And then vertically speaking, it's in equilibrium because it's not going into the surface or moving up off of it, so 0. All right, now, what was the question anyway? I'm just like doing a whole bunch of physics. Part A, draw a free body diagram. All right, we're good there. Since there was no friction, we didn't have to include friction because it said so. Part B, what is the normal force and why doesn't it equal mg? Well, I think we did a pretty good job of talking about that. So at this point, we could plug in our numbers and come up with an answer. I love when text just appears on the board. It's great. So 79 newtons then would be the normal force. Now, if we didn't have this force applied at an angle here, the normal force would have just been mg, 49 newtons. So please notice, if there's a force applied at some kind of an angle, the normal force can be different from just the weight of the object. So frequently, it's equal to the weight of the object, but very often it won't be. Okay, the last part of this question. Part C wanted to know what the acceleration of the object would be. And so then that's going to come to us from this equation right here. Given that there was no friction, that's a very simple calculation. Right? We can just plug in our 50, our cosine 37 degrees, and divide by the mass of the block, and we're going to end up with 8 meters per second squared. All right, if you want to check my math, you sure can, but frankly, most of the time, I'm not that interested, remember, in the numerical answer. Okay, what I'm more interested in is, can you set up the work? And remember, that means I want it to look like this. You're going to do it as symbolically as possible, which in this case is like the whole thing, except for the very end where you plug in the numbers. Okay, now, that's everything with example 5. Okay, so the main things that you ought to get out of that then would be, if you have forces that are applied at angles, they're going to appear in both equations. And so you have to be careful with that. Okay? So make sure if it's at an angle, it goes into both equations. All right, example 6 now. We're going to take the same question, but add in friction. And so everything is going to change. Let's get rid of this couch here. If we apply the force at an angle, and there is friction involved, then we'll add friction to our force diagram. And our x equation is going to be a little bit different. Right? It's going to be F cosine theta minus the friction force equals, well, now let's read the question. Example 6, draw a new free body diagram. All right, we're good. B, rewrite the equations describing the forces along each axis if the block accelerates at 1.5 meters per second squared. All right, so that means then that we are given an acceleration. So that means we're going to throw in ma over there on the right side. There's a related sort of question which we'll get to in the homework tonight, actually, which would be, what's the minimum force that you would have to apply to make the object move? So if it says minimum force, like it will in the homework, then don't put ma here. It's going to be just 0. Okay, because you're finding the minimum force required to get it moving. All right, the y equation will not change at all. Y equation is going to be the exact same thing. So x was different. Some of the forces in the y direction is going to be just exactly the same thing. Because friction doesn't have a y component, right? It doesn't do anything different. All right, now for part C, where we're supposed to determine the coefficient of friction, we're going to go back to the idea of friction is fun. And so something like this is going to happen in just about every question where you've got friction. You are going to sub in fun, right? Friction is mu times n. And then you've got to sub in something for the normal force. So that's going to be the standard process when friction is involved, is sub in fun, then sub in the normal force, which for this question is mg plus f sine theta. All right, so let's see what this equation here turns into when we do that. We have f cosine theta minus mu times the quantity mg plus f sine theta equals ma. Okay. Well, at this point, you could pretty much like start solving stuff. Like you could plug in numbers for all those things and come up with it. Again, because it's probably not very interesting to watch me type in numbers, we'll just go ahead and cut to what the answer for part C is. If after you type everything in, you get that mu is, I have it on here, 0.41. That would be the correct numerical answer. What the algebra would go like if you were doing this completely symbolically, though, would be something like this. I want to move the the mu stuff over to the other side. So over there we'll have mu mg plus f sine theta. I'm going to move the ma over to the other side. So now this side will have f cosine theta minus ma equals this, and then we divide. All right, and that must be the coefficient of friction, which works out to be 0.41. All right, now the last bit, part D, if we apply the force at an upwards angle instead. I'll draw this in green now. If you were doing this problem not symbolically, you'd have to like redo all of your calculations. Like if you went through the problem going like, all right, f cosine theta, mg f sine, all right, and then you've just had numbers going the whole way through the question, you would actually kind of have a lot more work to do. But since we did this question almost entirely symbolically, we're really almost done. There's only one thing we're going to have to change, and that's this. If we apply the force at an upwards angle instead of a downwards angle, the force is still applied to the right, so the x component won't change at all. Okay. The vertical component, though, is going to go from being down-ish to being up-ish. So in the same direction as the normal force. Therefore, that sign is now a plus, which means this is now a minus instead. So coming over here, now this is a minus. Oops, eliminate part of that g. All right, so now that's a minus, minus, minus. So the only change, as far as we're concerned, is going to be just a cascade of sign changes. All right, that's it. Now we would, if we wanted to, plug in our new numbers and we could get a new value. The question, though, just asks, like, okay, how is the answer affected? Like, does it go up? Does it go down? If we're pulling up, that should decrease the normal force. All right? If the normal force decreases, the friction force should also decrease. If the friction force decreases, then that means that the acceleration would have to increase as a result. So that would be our way of reasoning through that question. All right, some of the homework questions tonight are going to look very like this. The main difference being, it'll ask something like, what's the minimum force required to start the thing moving? That means this will be 0, and you'll have to factor out the force somewhere during the course of solving. Okay, part 3 now.